In this video, we're going to look at enthalpy changes, in particular the application of Hess's law and drawing Hess cycles to work out enthalpy changes indirectly. So first of all, let's talk about what is Hess's law. It simply states that the overall or total enthalpy change for any chemical reaction is always the same, and it doesn't matter, it's independent of the route that we take. So at A level, we're not actually normally asked to define this. It's not like other enthalpy definitions, which I have a separate video for. You don't have to sort of learn it off by heart. You have to apply it in lots of different contexts though. So the point of this video is to get you looking at it in lots of different ways and hopefully linking it to other parts of this topic and stuff that you've learned before, because actually at GCSE, we do learn Hess's law. You might just not realise that you've learnt it before. So what we should know about is these little things here, enthalpy level diagrams or enthalpy profiles. So on the left hand side, we've got an exothermic reaction, and I can tell it's exothermic because the products, CO2 and H2O, are lower in energy than the reactants, so that energy is given out, released to the surroundings. We have a downwards arrow. This is labelled energy change, which as far as I'm concerned for this video is basically the same as enthalpy change. Check whether or not your exam board asks for the difference. On the right hand side, we have our endothermic reaction, so the products, calcium oxide and CO2, are higher in energy, so that's going to take energy in. But both of these reactions, whether they're endothermic or exothermic, they both take in energy at the start and then release energy. And that's related to breaking bonds and making new bonds, which we'll have a look at in a moment with our calculations. The bonds might be covalent or they may be ionic in the case of, for example, calcium carbonate. And then our activation energy is labelled on both of them. It's from the reactants to the highest point in the chemical reaction, and that is basically related to the minimum amount of energy needed for a collision between particles to be successful for the reaction to happen. So what we should know about activation energy is we could use a catalyst to lower the activation energy. And we may be very used to sort of drawing an alternative profile. So for example, that green line on the right hand side is showing the same reaction in the presence of a catalyst. Not that I can actually think of a catalyst that would work for this particular reaction, but if it did, this is how we could show it, and we could see that the new activation energy, that's a shorter arrow, so less activation energy. But what we haven't done is we haven't changed this enthalpy change. A slightly more correct way to draw the catalysis pathway actually is something a little bit more like that. And what that's showing is a little intermediate stage. So when you do organic chemistry, you learn a lot about intermediates in the middle of chemical reactions. And so what we're saying is there's two steps to the reaction. So what we're saying is that the catalyst provides an alternate route or pathway for the reaction to take place. So this is where this is a tie-in with Hess's law. We know that catalysts do this, and we should know that catalysts don't change delta H. They don't change the overall enthalpy change of the reaction. Okay, we're also going to link this to bond energy calculations, which is part of the same topic as Hess's law. So here's a little simple bond enthalpy calculation just for a reminder on how to do them. They should be relatively straightforward. So we've been given the bond enthalpy values in the table, and we're going to use them to calculate the enthalpy change of this reaction here, which is adding hydrogen to ethene. So unless you're really confident, I recommend at the beginning you draw out all the bonds in a molecule. It's good practice anyway. And at the beginning of A-level chemistry, when we do this topic, we might not be that confident with organic molecules, so it is a good idea to see where everything is, because some typical mistakes that people make would be, for example, seeing C2H4 and thinking that there's 2 carbon-carbon bonds, or seeing H2 and thinking that that's 2 bonds. Of course, if there's 2 atoms, that's only 1 bond between them. Another thing to watch out for is that a C single bond C has a particular amount of energy as shown, and a C double bond C is not just twice that, it's a different amount. So then to calculate the enthalpy change, I'm going to add up all of the energies associated with the bonds in the reactants. So on the left hand side, we're going to break the bonds in the reactants. So I have 1 double carbon-carbon bond, 612. I have 4 CH bonds, 412, and I have 1 HH bond, which is 436. So I add all of that up, and that gives me a total of 2,696, and these are all in kilojoules per mole. And then on the right hand side for the products, I've only got 1 product, which is ethane, and that's going to be 1 single carbon-carbon bond and 6 lots of 412. We could actually have done no CH bonds on the left and 2 CH bonds on the right, but that's okay. This works fine as well. And that gives me a total of 2,820. And then hopefully we know that to work out the delta H, it's going to be the sum of the bonds in the reactants. So the bonds broken, which is 2696, minus the bonds that I make, which is 2820. And most people just learn this because it's not that hard to remember. But what does happen is, perhaps because we rote learn it, that when the question becomes a bit more challenging, a bit more applied, we then get a bit stuck and we don't actually know what we're supposed to do because it doesn't look like a normal bond energy calculation. So let's try and link this to Hess's law and also to enthalpy level diagrams. So how does this relate to an enthalpy profile? Well, this at the moment is just an energy level diagram. It's showing me that the overall reaction is exothermic. And actually, we sometimes get questions about why it's exothermic. So we did the calculation. We know it's minus 124 kilojoules per mole. Let's actually look at what we did in the calculation and how that relates to enthalpy changes. So what we did was we added up the energy needed to break the bonds in the reactants. So that value was 2,696 kilojoules per mole. But what was the product of that? So like this, what we're doing is splitting this reaction up into 2 steps. We're saying the first step is I take the ethene and the hydrogen and I pull apart the carbon atoms and the hydrogen atoms. And so what I will end up with is 2 carbon atoms and 6 hydrogen atoms. Imagine you've got those Molly-Mod kits at school and literally you've just pulled all of those grey bonds apart and you've got little piles of white and black atoms sat on your desk. Okay, so the reason they're gas is because we've broken all the bonds. Okay, so it's not graphite, it's not carbon or solid, it's literally just separate carbon atoms with no bonding. And the reason it's 6H is the same reason, right? It's not H2 because it's not hydrogen the element in its standard state. It is a very unusual state in which we've broken all the bonds, which is why it's such high energy. And then the other number that I calculated, the 2,820, was doing the opposite process to ethane, or rather the same process. So this number is the energy that would be required to go from ethane down here to the same middle point. So breaking it up would take in, because breaking bonds is endothermic, 2,820. So both of these arrows are going up. But when I actually do the chemical reaction, what actually happens is I break these bonds on the left-hand side, but I make the bonds on the right-hand side. And so actually the energy change that happens is the reverse. The energy change is minus 2820, and that's why I do the bonds in the reactants minus the bonds in the products. It's because the thing on the left-hand side is endothermic, and the thing on the right-hand side, the making of bonds, is exothermic. If we look at another example, really common exothermic reaction would be the combustion. So combustion of methane here with 2 molecules of oxygen. And again, we can do the same thing. We can work out the total bond energy for the reactants, which is actually 2640. The total bond energy for the products is 3338. I haven't put the actual values here. You can go and look them up and do this for yourself if you want. And then to calculate the enthalpy change, we would do this value minus this value, and that's because what we're doing is we're going to here, we're breaking up, so we've got individual atoms, then we're putting the atoms back together to do this, and our overall enthalpy change, delta H, is 2640 minus 3338, which equals minus 698. So the reason that we're doing this, let's get into how this links to Hess cycles. The direction of the arrows is the direction of the chemical reaction or process that we have been given the energy change for. We have been given bond enthalpies. The definition of a bond enthalpy is the energy to break a mole of a particular type of bond. So you start with the molecules containing the bonds and you end up with atoms. So we could also do this as what you might be more familiar seeing when we say a Hess cycle or a thermodynamic cycle or an energy level cycle instead of an energy level diagram. So we could write the chemical reaction that we're calculating across the top. 2H2O and CO2. At the bottom would be our gaseous atoms. Oops, did it wrong. I was thinking about elements. 4 hydrogen atoms and 4 oxygen atoms. So that's the same as what we've got here. The arrows point down, and that is because the values that I have been provided with are bond enthalpies. As we said, that's breaking bonds. So this is a positive endothermic value required to break those bonds, 4 lots of CH and 2 lots of OO, and on the right hand side we've got 4 lots of OH and 2 lots of CO, and the total value for that is my 3338. So when we learn this as an enthalpy cycle or Hess cycle, then we are trying to calculate delta H up here, and this is my direct route going from methane to water and CO2, or rather actually it's kind of just one arrow. A different way of getting there would be if I were to break all the bonds and then make them again. And so what you can see is I'm going with this arrow here. So I don't change the sign, it stays endothermic, but I'm going the opposite direction to this arrow. So I'm going to change the sign to make it a negative value. Okay, we don't normally write Hess cycles like this with bond enthalpies, so let's look at the more typical different examples. Before we do move on to that though, there's another thing I want to point out, which I think we're fine with bond enthalpies, but some reason when we do something else it gets harder and we find it harder to apply. These values, 2640 and 3338, they weren't individual numbers in a table, right? We had to use the numbers given, like 4 lots of CH and 2 lots of OO, 4 lots of OH, 2 lots of CO. We had to add them together. So numbers on an arrow, 2 things that we need to understand. The arrow is just an equation arrow. So it just goes from reactants to products. And the other thing we need to realise about that arrow is it could be more than one enthalpy change that we have to add together to get a total enthalpy change for that array. All right, let's apply that to Hess Law and diagrams. So very, very common is using enthalpy of formation. Make sure that you know your enthalpy definitions. You need to know formation, you need to know combustion, neutralisation. That's just for the first year, and then there's more to learn in the second year as well. I've got a separate video on those, so you can go back and check that, make yourself some flashcards. All right, so in this, we have been given enthalpy change of formation. Could just be called formation enthalpy. Lots of different ways. I've just represented it in this video as delta HF. They're all in kilojoules per mole, and this is for compounds. So in this situation that I have here, one of the things doesn't have a value, and that's because it is an element. So elements don't have enthalpy change values, or we can say that the value is 0. So that is because enthalpy change of formation is making compounds from elements. So in an enthalpy diagram, for example, if I wanted to make H2O, then what I would have is H2 plus a half O2 to make H2O. That's what value is represented by minus 286, which is up here. Okay. I'm not making one H2O though, I'm making 2. So we have to take that into account when we put the numbers into the Hess cycle. What's important is that all of these compounds can be made from their elements. So I'm going to put the elements at the bottom. The elements are going to be sulfur, they're going to be hydrogen, and they're going to be oxygen. So standard state. Sulfur, you are allowed to put just S in this situation. You may well have learnt that sulfur is S8. We do often simplify it as just S. However, hydrogen and oxygen, we want to keep the fact that they're diatomic, 2 atoms of each. We need to make sure it's balanced. It doesn't matter which side you look at, because the left-hand side at the top, this is the same as this. So long as the bottom has the same number of atoms, then we're all good. So this should be 3 sulfurs. I'm going to need 4 hydrogen atoms in total, so 2 H2s. That is gas. And then oxygen, I only need 1 O2 because I've got 2 here, or 2 on the left hand side as well. And that is a gas state. So in this situation, if we are given enthalpy of formation, because the definition is to make the compound from the elements, therefore the arrows go from the elements at the bottom to the compounds. Also, just like to point out, you don't have to write it with this at the bottom. There's any way you like that you could link these arrows together, including one of these situations. Okay, so either way it still works. We are going to put the numbers in the right place, so I recommend that you write everything out. So SO2 is minus 297. H2S, there are 2 lots of it, so I need to add on 2 lots of minus 20.2. On the right hand side, I've only got my water. Sulfur is not a compound, so I've got minus 286 times 2. And then I'm going to put that all together and actually work out what's going on. So that there is minus 572, and this arrow on the left is minus 337.4. So at the moment what I've done is these numbers are simply in the direction of those arrows. Those are the energy changes. So they're both overall exothermic processes. I want to know this enthalpy change here. To get from left to right using this alternative route, using formation, I would have to go against that arrow and with the same direction as that arrow. And so what I would need to do is change the sign of the one going down, but I would rather that we just write it in front. So what I mean by that is, if I say it's minus minus 337.4 plus minus 572. That might be a bit much, and you might be thinking, well, I'm obviously just going to put plus 337.4. Just remember the difference between the negative sign, which is just part of the enthalpy change, showing it's exothermic, and the negative sign, which is showing that we're going the opposite way to it. Overall energy change, therefore, is minus 234.6 kilojoules per mole. So that's how we use enthalpy of formation. Okay, now let's look at a slightly different one. And the only thing that's different here is we're not finding the value of the reaction across the top because we've been given it's here. So we know that this is equal to minus 334, and we're given two other values. And this time we're asked to find the enthalpy change of formation for HCl. Okay, so we can do the same thing. Because it's using enthalpy of formation in the table, then we can definitely put the elements at the bottom because that's what links them all. So carbon, natural state of carbon is solid, standard state of hydrogen, so 2 moles of H2 gas, and 3 Cl2 gas. So chlorine is diatomic, that's an element, again, it doesn't have a standard enthalpy of formation. So arrows going up from elements to compounds. Carbon and hydrogen to make methane is minus 74.9 according to my table. And then CHCl3 is minus 132. And then this is the thing that I'm trying to find. Now there are 3 moles of HCl. So if I knew the enthalpy change of formation of HCl, I would be doing 3 times that value and I'd be adding it to my minus 132. So what I'll do instead is use a bit of algebra and write plus 3x. Okay, so let's now write everything as an equation and then rearrange it to find x. So I'm going to show you a slightly different way to look at an enthalpy cycle, because previously we've just been going, okay, I want to know this arrow and therefore I go that way. And that's okay, but I actually have a slightly preferred way of doing it. I want to talk about this idea of direct, indirect. There are 3 arrows. Direct means I can go from A to B without going through anything else, and I'm actually going to follow the arrows. So if I actually start at my elements at the bottom, that seems like a sensible place to start. Like if I wanted to make anything at all, I could start with elements and literally do it however I want. So I could start with elements, make methane and chlorine, and then react them together to make chloromethane and HCl. Or I could go direct to chloromethane and HCl. So that means that this route, which I'm going to show with the red arrow, that's very confusing, isn't it? Because I've already used red up there. Let's not do that. Let's do orange. This route here is equal to the other 2 added together. So if I put in the numbers, minus 132 plus 3x equals minus 74.9 plus minus 334. You can use brackets if you want, and I quite like that actually, because what I'm doing with the brackets, obviously the calculator does not need them, and you might not either, but the bracket is showing that this is the energy change, enthalpy of formation of all these individual compounds, plus the enthalpy of the actual reaction across the top. It is not what I'm doing to the enthalpy changes. The plus in between the brackets is what I'm doing, adding them together. So now I can rearrange it by adding 132 to both sides, and I get 3x is minus 276.9. You might be like wanting to rearrange it all, put it all in, divide by 3 all at the same time in your calculator. If you're confident with your maths, that's absolutely fine. But at the same time, if this was a 3-mark question, you would lose all the marks if you got the wrong answer just by a tiny little calculator slip. So that's why I would prefer to write everything out in terms of what you're trying to find in terms of x. There's going to be a working mark for that. There's going to be a working mark somewhere in this question for finding 3 times the enthalpy change, the minus 276.9, before you divide it by 3, just in case, again, something goes wrong when you type it in. So do your working whenever you're doing these Hess cycles. Okay, what about using enthalpy of combustion? So that was 2 different ways of using enthalpy of formation. Enthalpy of combustion is a common one because it's something that we can measure in laboratory. I've got a slightly different version here because what I've got is a compound that contains sulfur, and normally we just have carbon, hydrogen and oxygen, so I thought I'd throw one in using sulfur just to show how we would do it. And it says calculate a value for standard enthalpy of formation. So another reason I've used this example is because if you learn, oh, when it's formation, the arrows go up, and when it's combustion, the arrows go down, which is true, but if you don't know why you're doing that, you can easily get a bit confused when the question is asking you to find formation using combustion or find combustion using formation. Make sure you know what's going on. So the value I'm trying to find is enthalpy of formation. So good practice is to write that equation for that across the top. So to write an enthalpy of formation, put the product on the right hand side first, because I know what that is, and then go back and put the elements in. So 2 lots of carbon. Use clues in the question. It does actually give you the state symbols for the elements on the top there. Plus, I'm going to need 3 lots of hydrogen, so to be careful of formulae where the hydrogens are shown separately. So this is, you can see this is basically just the same as ethanol, but with a sulfur instead of an oxygen. So I'm going to have 3 lots of H2, and I'm going to have 1 lot of sulfur, which is a solid. And then at the bottom of the Hess cycle, we need to know what they have in common. So when things burn, we are going to add oxygen to both sides. Now I'm going to need a certain amount of oxygen, but it doesn't actually matter about that bit when I'm doing the Hess cycle, because we're just going to burn it in excess oxygen, because that's what enthalpy of combustion means. So if I burn carbon in oxygen, I will make CO2, and because there's 2 carbons, I'll make 2 CO2s. When I burn hydrogen, I'll make H2O, and because there's 3 hydrogens, there's 3 waters. And when I burn sulfur, I'm going to make SO2 as well, and that's a gas. Right, so basically it's all balanced. I don't really need to look at this side because it's got the same number of carbon, hydrogen and sulfur, so it's going to make the same thing when I completely combust it. I could work out how much oxygen I need, really, I suppose. 4 plus 7, 8. I need 9 oxygens, so I need 4.5 oxygens. But basically I would just be putting the same amount of oxygen on both sides, so there's no real point in doing that. It cancels out. It doesn't give me anything extra in terms of enthalpy changes. So then we have an arrow, and the arrow now is going down, and that is because when I burn something, the products are what you get after you've reacted with oxygen. So these are the products, whereas in the enthalpy of formation, the compounds were the products and the elements were the reactants. Now it's going the other way because the definition is different. So on the left-hand side, I've got minus 394, and that's times 2 moles of carbon being burned, 2 moles of hydrogen being burned, minus 286 times 3. And then I'm also burning sulfur, so be careful because elements can combust. They don't have enthalpy of formation. They do have enthalpy values for combustion. And so I'm going to add on my minus 297. On the right hand side, I've just got 1 mole of that, so all I have to put is that value there. Also recommend, when you've got lots of numbers like we have on the left, add them all up, just so that Again, you get that working mark. If you do happen to have a little slip on the calculator, at least you get all of the following marks correctly. So I'm going to use my direct-indirect method again. So what do I mean by that? There are two ways that I can get from my elements, we're starting with elements again, to the CO2, H2O and SO2. I could either make this ethane thiol thing and then burn it, or I could just go straight and burn all of those elements. So the red arrow is the same enthalpy change because I'm following the arrows in the same direction. I'm starting here, I go forward, I go forwards. Starting here, I go forwards. So this is the same idea as reversing the arrows. In fact, I'm going to show you it both ways. So if I did it like this, this is the calculation I would write. Delta H plus minus 1170, that's my red root, equals minus 1943, which is my downward arrow on the left hand side. So direct root is minus 1943. Indirect root is the enthalpy change I'm trying to find, plus minus 1170. Rearranging that to find delta H on its own, I get delta H is minus 773. Differently, how else could I do it? So if you're more happy about reversing arrows, let's see how we would do it like that. If you want to reverse arrows, you want to find delta H and you're going from there to there. Okay, so delta H equals minus 1943, which I've just kept the same because I'm going with that arrow there. And then this arrow, I'm going the opposite direction. So I'm going to put a minus in front, minus 1170. Switching the sign. Guess what? Answer's the same because it's Hess's law. And it doesn't matter how you work it out, so long as you have the right idea. Okay, let's have a look at some less predictable things. Okay, so we've done combustion, we've done formation. Now we're going to look at some other applications. So here is one where I'm trying to find this value up the top here. So delta HR, delta H reaction. Okay, it's not formation or combustion. It's the reaction of NO2 to produce nitrogen and oxygen. It's almost like the reverse of enthalpy of formation, actually. Okay, so let's write that across the top because I know that's something I'm trying to find. That's the mystery enthalpy change. Okay, then I've been given two other values, and these are not sort of any sort of specific values. Okay, these are just sort of two other chemical reactions. But what I can do, here is the strategy, is look for things that you already have in your Hess cycle and sort of cross them off. So NO2 is over here, N2 is here, and O2 is here. Now have a look at what's left. NO and O2. That's the same in both of them. Cool. That's what I'm going to put down the bottom then. 2NO plus O2. All right. Now let's construct it. We need to work out the arrows. So the arrows here, remember they actually have a direction already. They already know where they're going. So the first arrow, which is 114.4, is going from NO2 towards NO and O2. So that is this arrow here plus 114.4. The other arrow, minus 180, the other reaction, is going from NO and O2 to N2 and O2. So that's this direction, minus 180.8. So actually, this is a lovely little Hess cycle. We're just going from NO2 into NO and O2, and then to N2 and O2. I'm not changing the direction of either the blue or the green arrow. So delta H is just going to be plus 114.4 plus minus 180.8. Again, I'm being super laborious and putting my signs in. You will thank me when you don't make the mistakes in the exam, trust me. Don't care if it seems like a bit much. Just want to separate the numbers from what you're doing. You're just adding them together because we are going the same way. Could have probably done that without a Hess cycle. As you get more confident at it, that's fine. Right, last thing we want to look at is linking to experiments. Okay, so obviously we can do enthalpy change experiments, and there's a whole video on that on my channel as well. So you can go and have a look at how we would do combustion, we can measure neutralisation, we can measure things like displacement, redox reactions, lots of different ways, dissolving. So there are loads of things we can do where we can measure the temperature change and then find the enthalpy change from that. But many things we can't do directly. And here's an example where we can't. So magnesium carbonate, when you heat it, it breaks down and decomposes. But you have to heat it with a Bunsen burner. It's very endothermic. And so you can't use this reaction to heat or cool down any water. You've got nothing that you can stick a thermometer in. You can't stick a thermometer in a pile of magnesium carbonate solid because you're heating it with a roaring Bunsen flame. So it's impossible to measure this directly using that kind of experiment. So we need an indirect thing. We want to be able to do something the same to each side. So in the combustion, what we did remember was we added oxygen to both sides. Like that was because we had things on both sides of our equation that would burn. Now this isn't going to burn, okay? Magnesium carbonate is an ionic compound. They don't burn. And so we can't add oxygen. So what else can we do? Well, magnesium carbonate is a base. Magnesium oxide is a base. What I can do is add acid to both of them. So if I did that, magnesium carbonate, let's say we add sulfuric acid. Sulfuric acid makes magnesium sulfate plus H2O plus, what am I doing? Plus CO2. I was thinking of the sulfur from the last one. I could also take magnesium oxide, add H2SO4 to that as well, and I will get magnesium sulfate, salt, and just water. Okay, so how does this help? Well, I could do that in a polystyrene cup, and I could measure the temperature change, and I could work out an enthalpy change in kilojoules per mole. So if we use that same process that I just had, where we cross out anything that is already included in my top equation, magnesium carbonate, magnesium oxide, and CO2 is kind of already on the right hand side, but can you see that what we have is we can add sulfuric acid to both sides of this equation and end up with the same product. So if I added H2SO4 to magnesium carbonate, arrow goes down, reactants to products. The products are MgSO4, H2O, and CO2. If I add H2SO4 to this side, to the magnesium oxide, I'll make the same products, magnesium sulfate and H2O. Now the CO2 isn't there, but it's here already. So essentially what I have is CO2 going to CO2. So there's no enthalpy change associated with that, so it won't change my numbers. In the same way that if I, for example, had oxygen and I just added more oxygen, it wouldn't change the enthalpy change. It would just be there to balance. In the same way, I don't need to write the sulfuric acid on both sides. It's the same way as if I was doing combustion, and I don't necessarily have to write the oxygen. It's the same amount of sulfuric acid, same number of moles. So the enthalpy change, let's say that we did the experiment and we found out that To add it to carbonate, you get an enthalpy change of minus 52 kilojoules per mole. Notice these numbers are much smaller than combustion. And let's say I did it on the other side and found that adding it to magnesium oxide was minus 149 kilojoules per mole. And then we can just use our method. I'll go back to this one, which is delta H. Let's do it in green. Delta H is minus 52, because I'm going with that arrow, minus 149. And I end up with plus 97 kilojoules per mole, which is endothermic, which is what I'm expecting, because remember, that's why we couldn't measure this energy change, because it's very endothermic and you have to heat it with a Bunsen. So many of the things that throw students are just adding the same thing to both sides. So here's another example where we're just given two energy changes and we're expected to find this one here. Right, so these are all displacement reactions. These are all metal plus metal salt, and you can see all the metals are swapping places. We could have this as an ionic equation because the sulfate ion actually isn't really doing anything. But let's not worry about that right now. Let's worry about how we put it in a Hess cycle. We know we've got two numbers. You may have realized by now, you kind of got the idea that you're going to have to do one of these numbers, take away the other, right? The only thing you need to know is which way round does it go? Is it the minus 530 take away the minus 219, or is it the other way round? Okay, so let's use the same technique. This is the equation I want. That's the one I'm trying to calculate. Find the things in that equation. So zinc sulfate, boom. Magnesium, boom. Zinc, boom. Magnesium sulfate. Okay, what have I got left? Copper, and copper sulfate is the common denominator kind of thing in this reaction. So what I've got is a reaction where I add copper sulfate to zinc. That's the top reaction. And I've got a reaction where I add copper sulfate to magnesium. And here I've got magnesium and I've got zinc. So if I add copper sulfate to magnesium, I'll make magnesium sulfate and copper. Arrow down. Also, just like before where we had something that was the same on both sides, I've also got some zinc sulfate here, right? Because it's already here and I can't get rid of it. So if I took a mixture of zinc sulfate and magnesium and added copper sulfate, I would end up with magnesium sulfate, copper, and zinc sulfate. All right, and then what about if I added copper sulfate to my zinc? Well, guess what I'd make? Zinc sulfate and copper. That's here. And the magnesium sulfate is already here. So it all balances out. Basically what we're saying is that this minus 219 is the enthalpy change when I displace copper with zinc, and this one is when I displace copper with magnesium. The magnesium one is on this side, minus 530, and the copper one, whoops, is on the right hand side, which is minus 219. We're going that way, so delta H is minus 530 minus 219, which is minus 311. Now if I had done it the wrong way round, because we know it's just going to be one take away the other, I would have got an answer of plus 311. Now if I got an answer of plus 311, I would hopefully be super suspicious, because why would two of these displacement reactions be exothermic and the other one be endothermic? Okay, that's not how it works. The other thing that you might realise from GCSE is a nice little link here to those little experiments that you did where you measured the reactivity of metals using the temperature change that you got during the displacement reactions. So can you see that this is telling me Magnesium is the most reactive because you get the biggest enthalpy change when you add the magnesium to the copper compared to the zinc. And of course, copper is the least reactive, which is why it's getting displaced by all of them.